So in this video we're going to take a look at solving basic cosine equations that involve stretches and compressions and translations. So the first example, it says find in radians the roots of g of theta equals 2 cosine theta plus the square root of 2 on the interval from 0 to 2 pi. So the first thing we need to recognize is that when we're asked to find the roots, we're being asked to find the zeros of the equation, or where the equation is equal to 0. And those are going to be the places where we cross or intersect the horizontal or input axis. On the interval from 0 to 2 pi, based on the graph that I've included here, we can see that there are two roots, two places where the function is equal to 0. And if we look at the toolbox function cosine of theta, and we notice there's no multiplier on theta, we should kind of expect two roots, because on the unit circle there are two places where the toolbox function cosine of theta is equal to 0. One is at pi over 2 radians. That's where we have an input of 0 giving an output of 1. That's at the 90 degree or pi over 2 radian mark. And on the interval from 0 to 2 pi, if we walk past there to 3 pi over 2, we also get a place where the x-coordinate is 0. So we would expect, as long as no multiplier is being applied to the input variable, we would expect that we might get two roots to an equation that involves just the cosine of theta. When we start doing multipliers on theta, that changes things. So to find the two roots, what I want to do is to set the equation equal to 0. And what my approach is going to be is to find all solutions and then use that to find the specific solutions I want in the interval of interest. There are other ways to do it, but I like to focus on doing it with this technique. So I set my equation equal to 0 so I can figure out when the function is 0. I want to isolate the cosine function, and to isolate the cosine function I will need to subtract the square root of 2 from both sides. And once I have done that, it will leave 2 cosine theta on the left hand side, so I'll need to divide both sides by 2, because 2 divided by 2 will be 1 cosine of theta. So I'm going to divide both sides by 2, leaving me with cosine of theta. Now to dig theta out of here, I'm going to use the cosine inverse on both sides. So I'm going to get theta equals the cosine inverse of the square root of 2 over 2. And what I want to remember from video 3 in this particular series is that when I get the principal solution by taking the cosine inverse and getting that angle that is between 0 and pi radians, because the cosine inverse always gives us an angle that is between 0 and pi radians, that there is another angle that generates the same side ratio that is the opposite of this result. So we always get plus or minus the standard solution. The cosine inverse gives us an angle. We get plus or minus that angle as two possible solutions. And then what we want is every angle that is coterminal with these two angles. So we add to this plus 2 pi k, and that will get us all of the coterminal angles as long as k is an integer. K has to be integer. 0, plus or minus 1, plus or minus 2, etc. So this is all solutions. And then what you want to do is look at the side ratio and identify, is that side ratio, there should be a negative on there, is that side ratio, negative root 2 over 2, associated with a special angle? And in particular, is it associated with a special angle between 0 and pi? Because the cosine inverse only gives us angles between 0 and pi radians, or 0 and 180 degrees. And negative root 2 over 2 is going to correspond to the angle 3 pi over 4 in quadrant 2 that has the ordered pair, negative root 2 over 2 comma root 2 over 2. And we want to remember that on the unit circle, the cosine of theta is the x-coordinate on the unit circle. So now I can make a replacement. I can say cosine inverse is 3 pi over 4, but negative 3 pi over 4 generates the same output. If I go over here to, here's 3 pi over 4, if I swing through negative 3 pi over 4, I also get an x-coordinate that is negative root 2 over 2. It just happens that the y-coordinate is also negative in quadrant 3. So I get two angles that generate distinct side ratios in the sense that there are different locations on the unit circle, and then I get plus 2 pi k for all of my coterminal angles, and this is all solutions. But I'm asked to find the solutions on the interval from 0 to 2 pi. So what I want to recognize is that plus 3 pi over 4 is an angle on the interval from 0 to pi. So in fact, if I let k equal 0, I see that I'm going to get theta equaling 3 pi over 4 plus 3 pi over 4 plus 2 pi times 0. Well, that's just going to give me 3 pi over 4 as one of my solutions. And then if I take the negative 3 pi over 4, which is an angle somewhere over here, and I let k equal 1, I'm going to get theta equals negative 3 pi over 4, which is not on the interval from 0 to pi. But if I add to that 2 pi times, put k equal to 1 in, 2 pi times 1 is 2 pi, and get my common denominator 4 over 4. I'm going to get 4 times 2 is 8 pi minus 3 pi is 5 pi over 4. That actually corresponds to this angle here on the unit circle. 3 pi over 4, 4 pi over 4, 5 pi over 4 also gives me negative root 2 over 2. So this is one where we could use the unit circle and special angles to get our two solutions. But part of my purpose for this video is to get us to practice finding all solutions to these types of equations. So the next example, the equation is identical with the exception that it's 2 pi instead of pi. And we still want the roots on the interval from 0 to 2 pi. So we're still asking, where will g of theta equal 0? And what I want to recognize is that a multiplier of 2 on the input variable makes everything happen twice as fast. So if the cosine of theta, which was involved in the previous function, generated 2 roots, if I'm going twice as fast, twice theta, I expect to get twice as many roots, or 4 of them. And when I look at the graph of g of theta here, I see that on the interval from 0 to 2 pi, I am indeed generating 1, 2, 3, 4 places where g of theta is equal to 0. And that is because this multiplier of 2 is going to give you double the solutions that we got the last time. We're doubling the speed at which we get our inputs. Solution process is the same though. We just take our equation. We are after the roots, so we set our equation equal to 0. We then isolate the cosine function, and we do that by subtracting the square root of 2 from both sides and then dividing both sides by 2 to isolate the cosine of theta. We then take the cosine inverse of both sides, which will free the twice theta. I hate when I do that. We're working with twice theta. This is cosine of twice theta. So this will free the twice theta. I'm going to get the cosine inverse of negative root 2 over 2. This is the angle that generates a side ratio, negative root 2 over 2. And every angle coterminal with this angle generates a side ratio of negative root 2 over 2. So I'm going to go plus 2 pi k. And I'm going to recognize that I not only get plus that angle, but I get the opposite of that angle as an angle that generates the side ratio, negative root 2 over 2. Once I've done this, I then isolate the theta, by multiplying both sides by a half. So I'm going to get theta equaling plus or minus a half of the cosine inverse of negative root 2 over 2 plus a half of 2 will give me pi k. And then we want to look at this and say, is this a side ratio that corresponds to a special angle? And it is. We saw on the previous slide that angle generated this guy right here, 3 pi over 4. The cosine inverse of negative root 2 over 2 is 3 pi over 4. That's the principal solution, plus r pi k from right here. And then this simplifies just a hair. We get theta is either plus or minus 3 pi over 8 plus pi times k. So I want to recognize that if k is equal to 0, I'm going to get a solution positive 3 pi over 8. So theta equals, for k equals 0, I'll get a solution. And then for k equal to 1, I should get an additional solution. So if I do that, I'm going to go theta equals, it's going to be the positive, so 3 pi over 8 plus either pi times 0, or I'm going to get 3 pi over 8 plus pi times 1. But pi times 0 is 0, so 0 plus 3 pi over 8 is just 3 pi over 8, comma, here pi times 1 is pi, but I would still need to get a common denominator, so I would multiply by 8 over 8, which will give me 8 pi plus 3 pi is 11 pi over 8. And then I'm going to work with the negative 3 pi over 8 and recognize I need to add a pi to that to make it positive. So I'm going to say for k equal 1, and I need to generate two solutions, so k equal 1 or 2. Take and plug in theta equals negative 3 pi over 8 plus pi times 1 is pi, or negative 3 pi over 8 plus pi times 2 is 2 pi. Get our common denominators. I've got an 8 sitting down here, so I need to multiply by 8 over 8. So I'm going to get 8 pi minus 3 pi is 5 pi over 8. Or I'm going to get the common denominator, I'm going to get 8 times 8 over 8 is going to be 8 times 2 is 16. 16 minus 3 is 13 pi over 8. So my solutions are, if I put them all together, theta is either 3 pi over 8, which is going to correspond to this point right here. Here's my 3 pi over 8, comma, my 5 pi over 8. Which is going to correspond to this point right here. This is going to be at 5 pi over 8. And then I'm going to get 11 pi over 8, which is going to correspond to this point right here, 11 pi over 8. And I'm going to get 13 pi over 8 as another spot on the interval from 0 to 2 pi that generates a 0 for the function.